101s. We talked about cells that make up the alveoli, type 1 and type 2 cells, surfactants role and all that. What else did we talk about? Started talking about gas properties, Dalton's Law. I was going to say Doyle's. Dalton's Law. Anybody have questions about what we went over last time? Yeah? It's produced and secreted by the type 2 cells. What the actual molecules are that make it up, I'm not quite sure how that is sort of formed from type 2 alveolar cells.
They do anywhere else in the body?
Not that I'm aware of. Anything else? Just got it. All right, so we just had previously talked about Dalton's Law. Right? All the partial pressures of gases in the atmosphere add together for the total atmospheric pressure. That's what Dalton's Law told us. Then there's gas movement. How you get gases to move from one area to another. Really, you can think of this as how you make wind. So gases are going to go from high pressure to low pressure. It's another gradient. So if you've got in some atmosphere a high pressure area and a low pressure area, that air will move from the high pressure to the low pressure. We actually live in a really good place to sort of demonstrate this in the San Francisco Bay Area, especially in the springtime, let's say late springtime through the summer. The whole San Francisco Bay Area really represents this well. So let's go ahead and take a look at it. So here is a map. We're out here, and we're going to compare San Francisco to Sacramento, the Central Valley. So where is that? Central Valley is going to be all right up in here, so some of this brown section. All right, so let's imagine a typical late spring summer day. As the day gets going, what happens in Sacramento? Let's say in the middle of the summertime. Hot. I would say uncomfortably hot. Compared to San Francisco, right? How's the temperature in San Francisco? The same. It's not cold, it's cool. I keep telling my wife that she's from Phoenix, Arizona. It's cool, right? It's totally different than cold. All right, it stays cool. All right, so Sacramento gets warm. What happens to the air in Sacramento? Expands and rises, yeah. So that's what the little red squiggles represent. All that warm air that's heating up during the day is going to rise up. And so what happens to the air pressure in the Central Valley? You just removed a bunch of gas.
It's lower.
It's lower. The air pressure drops. But the air pressure out here doesn't drop, or it drops very little compared to the Central Valley. So you have a relatively higher pressure on the coast, a lower pressure in the Central Valley, and then what happens? Air is going to move from high pressure to low pressure. And so that's what these blue arrows represent. That air that's coming in through the gate. And in this summertime, if you go down right to the marina and you look out there in the, like right around noon, you see a marine layer out there. And things are sort of set up typically. That thick fog that's right outside. And as the afternoon progresses, that marine layer moves in. And you can literally see a wall of fog as it engulfs the Golden Gate Bridge and comes in, and all of a sudden it's really cold and everything's damp because the fog moved in. The hotter it is near Sacramento, the further in that marine layer moves. And so it's getting sucked in by this pressure gradient. Lower pressure near Sacramento, higher pressure San Francisco. And that moves all the way in, and then once the day's over, that marine layer backs out again, and you do it all over the next day. And so that air is moving because of the pressure gradient. Same thing's going to happen in our body, obviously to a less extent. The same thing happens. Okay, questions about that?
But Sacramento don't have any wind. We have wind here.
What's that?
We don't have. They don't have any wind in Sacramento. All the wind is here.
No wind in Sacramento? Have you ever seen wind there?
No wind. Yeah, like they maybe a little bit in the morning, but I don't see anything like that. Seldom. Mostly here is windy.
It can be very windy here, but I mean, you can have breezes there, right? So you're not going to get as much wind necessarily as you might get, say, right underneath the Golden Gate Bridge. It just screams right through there. It's also the funneling action. But you're going to have even small scale pressure gradients within that area, so it's not just one steady pressure gradient. And anywhere there's a pressure gradient, you're going to get air moving, you're going to get a breeze. So yeah, it can come in either breezy there. Right? Even in the whole delta leading up to it. It's really when people sail there all the time, those sails are using wind. Right? So it, how windy it is, it varies throughout that area. It depends on lots of different things, but okay, anything else? All right. So we had Dalton's law, we had gas movement. The third one I wanted to talk about was Boyle's law. Boyle's law. All right, so what does Boyle's law tell us? It tells us that the pressure of a closed system is inversely proportional to the volume. So the pressure and the volume are inversely proportional to each other. And this is for a closed system. So when we say closed system, it's sealed off. There are a fixed number of gas molecules inside. So let's look at an example. Demonstrate this. All right, so we've got this magical beaker of purple spheres. And there's a certain number, each sphere represents a gas molecule. A certain number of gas molecules, I don't know how many are in there, we can count them, but it should be the same between the two. And let's say at time 1, that's what the subscript 1 represents, we have some volume, and there's some pressure in there. Those gas molecules are bouncing around, exerting a pressure on their surroundings. Let's say over time, we decrease the volume, we squash that down to the volume at time 2. And we've got the same number of gas molecules in there. What happened to the pressure when we reduced the volume? The pressure went up. All those molecules are going to bounce into each other more often now that they're stuffed in a smaller space. So if volume goes down, the pressure goes up. You can go in the other direction. If the volume goes up, the pressure goes down. All right, another way to write that. Again, let's think of these subscript numbers as two different times within the same system. So the pressure at time 1 multiplied by the volume at time 1 is going to equal the pressure at time 2 multiplied by the volume at time 2. So the pressure times the volume has to be equal over time. Let's go ahead and put some numbers in just to see this in action. So let's say we start with 1 liter at 100 millimeters of mercury for pressure. And we're going to change the volume to half a liter. So at time 2, we cut the volume in half. What would the pressure be? 200 millimeters of mercury. Right? So if you have the volume, you double the pressure. Right, this one's going to be, this relationship is going to be really important in ventilating our lungs. How we get air to go in and out of our lungs. Okay, everybody got that?
Not yet.
This law only is for the lungs.
Well, this works, as far as we know, anywhere in the universe where there's a closed system, where we have a fixed number of gas molecules without varying temperature.
But the pressure is also based on the density of the molecules, because sometimes the density of the molecules is not go that much close to each other. Imagine that is like not, for example, not any gas can have the same density. And if you bring it out, its formula should be like multiply some density to show the density of different gases, because this is the very general.
Well, so the density of something is the mass of something in a given volume, right? And so we're holding the mass constant, and we're changing the volume, right? So there's density sort of, in a way, included in this. Because it's a closed system, we're saying that the mass is not going to change, and we're going to be playing with the volume. So yes, the density will change, and how is that expressed? In changes in pressure. So yeah, it's going to be a little different from one gas to another in terms of how much pressure there is and volume and all, but if you keep the number of gas molecules constant, don't let the pressure or the temperature change, then this relationship will hold for whatever the gas is.
But I try to say that density is not flat wave to the change, exactly like sometimes is a wave like this change, like angle like this. Like
So
this
the density doesn't change linearly?
No, just like sometimes it change like
With what relationship?
based on the material, like what kind of density we have, like what kind of gas we have or liquid we have. Because
So this nonlinear curve.
Multiply V, like something like that, to show the density, to show the what material we use.
Let's go back to your curve that's not linear. Okay, so I assume density is the horizontal axis of this graph, is that correct?
Not horizontal, like as you said, like it's like graph is going to be like something like a straight, and but it's not a straight. It should be like something angle, like it's going to go up or down based on the what kind of thing, gas or material you use. It's not the same as they said here. That is like a general, like it said blue blood and red blood for the artery and something like that. You said use it for general for the high primary school. Kind of same as it say here. Like you said use the blood for arteries.
Right. Well, I know that. Yeah. I mean that's
kind of similar like that. This is very general.
Well, it is really general, but this relationship holds with, well, at least with atmospheres. So maybe there are some strange gases out there that behave differently, dramatically differently. But if you look at atmospheric gases, this relationship is going to hold. Volume relative to pressure. So I guess we could say under biologically relevant conditions, this holds. Will we accept that? We still don't like that.
Yeah.
So what do you know of specific gases that don't behave like this?
No, but I know this formula is very general. It should be multiplied by like something like a formula is like this, like consider as a density or material to make it complete, because this one is not complete. But this is enough for this class.
You're okay with this in this class?
Yeah.
Everybody else okay with it?
Yeah.
Okay. There's more to the story apparently. All right. So the simplified version, right? Volume, when you decrease the volume, the pressure is going to go up. Right? When you increase the volume, the pressure is going to go down. And again, we're going to use that with ventilation. We'll talk about ventilation. Okay, so we saw this before. The different forms of respiration that we're going to talk about. We're going to first go over ventilation, and there's external gas exchange and internal gas exchange, and then there's gas transport. We're going to try and get through. All right, let's start with ventilation. And how are we going to get air in and out of our lungs? So we need to get air flowing through the airways, and so keep in mind that the flow is proportional to the change in pressure over the resistance to airflow through the airways. Sure, the flow of air through our airways is proportional to the change in pressure. So the bigger the change in pressure, the faster air is going to flow, over the resistance to flow. We talked a bit about resistance already, right? Like the diameter or the radius of the airways is going to change resistance to flow. We even went over that with blood vessels, same idea. Okay, let's go ahead and look at the pressures involved here, right? Because the change in pressure is going to be important. So what are the ventilation pressures? Well, for one, the pressure in the atmosphere, atmospheric pressure. That's the pressure that air exerts on our bodies all around us. We also need to look at alveolar pressure. That's the air pressure inside our lungs, in those air sacs. And there's one other pressure that we need to pay attention to, and that's the intrapleural pressure. Remember, the pleura are those membranes of the sacs that surround our lungs. And those membranes are made of two layers. One layer is stuck to our lungs. One layer is stuck to the lining of our thoracic cavity. And those two layers are stuck together with that thin layer of fluid between them. And in between those two layers is a pressure. That's going to be this intrapleural pressure. So we're going to pay attention to that as well. Here's a little drawing showing this. So this darker blue represents our lung. The light blue two lines represent the layers to that membrane. and there's that space in between the two, which is really, really small, but that's where that interpleural pressure will be measured. Everybody feel good about these pressures? Know what we're talking about? All right, let's go ahead and look at inspiration first. How are we going to get air into our lungs? So just think about sort of general overall, how are we going to do that? Some animals actually push air into their lungs. Do we get to do that? No, we don't push air into our lungs. All right. There are, for instance, kind of sort of amphibians like frogs can push air down into their lungs. But instead, we suck air into our lungs. Okay? So we suck air into our lungs. We've got to create this pressure gradient between the atmosphere and what's inside our lungs. Right? We could increase the pressure in our atmosphere. That's kind of hard to do. Or we could decrease the pressure in our lungs, which is what we end up doing. Think about Boyle's law. How are we going to apply Boyle's law that way? The general version of Boyle's law, right? So if we're going to create a lower pressure inside our lungs, what do we do to the volume of our lungs? You want pressure to go down, the volume's got to go up. So if you can make your lungs bigger, you'll drop the pressure in there, and now air can flow in, or you can suck air into your lungs. And so that's what we end up doing, right? We expand our lungs to drop the pressure, to have air flow in. All right, so we need to do that somehow. So our lungs, do we have little muscles in our lungs that can push the walls of the lungs out? No, we don't. They're just these elastic bags, right, or sacs. So remember, though, that these lungs are stuck to the walls of our thoracic cavity and stuck to the diaphragm in the bottom. So if we can move the walls of this cavity out, the lungs will follow, cause our lungs to increase in volume. Does this make sense, everybody?
Yeah.
Questions so far? Not yet? All right. So we need to somehow expand the thoracic cavity. How are we going to do this? Well, we contract our inspiratory muscles. This is an active process. To get air into your lungs, you need to expend energy. It takes energy to get air into your lungs. So what are we going to contract? One of the muscles is the diaphragm. Remember, that's that dome-like muscle underneath your lungs. When it's relaxed, it's in a dome shape. And your lungs are stuck to that muscle. When that muscle contracts, it gets shorter. And so the dome flattens out. And when it flattens out, it pulls the bottom of your lungs with you, or with it. We also contract our external intercostal muscles. So the muscles between our ribs, right? The outer layer of those muscles, when they contract, they pull our rib cage up. Right? But how does that make our thoracic cavity bigger? Well, when your ribs get pulled up, they also swing out. To visualize that, you can imagine a paint can. That's kind of a paint can. It's got a crushed bottom, but you get the picture. So the paint can is going to represent our thoracic cavity. The handle represents our ribs. So that's when we're nice and relaxed. If we're going to inhale, we contract our external intercostal muscles. We're going to swing the ribs, or in this case, the handle up. When we do that, right, this distance increases. Right? When you swing the ribs up, or in this case the handle up, it also swings out. Right? This part of the handle is now further away from the can than it was. And so when the ribs are at an angle also, so when they get pulled up, they swing out. And by swinging out, it increases the volume inside your thoracic cavity. Your lungs move out with it, and they get bigger. Questions about that? All right. So in this diagram, so the diaphragm here contracts, pulling the bottom of the lungs down. External intercostal muscles contract, pulling the ribs up and out, which causes the sides of those lungs to move out. So we increase the volume, we decrease the pressure. We've got a pressure gradient, so air flows into the lungs. Okay? All right, so that's inhaling, active process. You have to contract muscles to do it. All right, expiration. How are we going to get air out of our lungs? This can be easier. This can be a passive process. It doesn't take energy. You don't have to use more energy to get air out of your lungs. All you really need to do is relax your inspiratory muscles. So when you relax your external intercostal muscles, those ribs will swing back down and in. When you relax your diaphragm, why would your diaphragm pop back up? Why wouldn't it just sag down when it relaxes? It's attached to what? Okay, it's attached to your lungs, so why don't your lungs sag back down with the diaphragm? Because what? You got guts down there. There's stuff in the way. It's not a big open cavern. So there's stuff down there. And why else?
The membrane, the pleural, that holds them together.
Pleural membrane? Well, that's going to make sure the lungs and the diaphragm stay together.
The pressure in the lungs needs to expand.
Well, you just inhaled, right? And you expand your lungs and drop the pressure, air flowed in until that air pressure in there equilibrated with the atmosphere. So now there's no difference in air pressure. But what about your lungs, right? If you took fresh lung tissue and you stretched it out and let go, what would happen? You would go back. So you have elastic tissue in your lungs. So your lungs are constantly trying to recoil and shrivel up. They can't shrivel up because they're stuck to the thoracic cavity wall and you can only get that cavity so small. But it's constantly trying to pull in. So if you had that diaphragm flattened out, when you relax the diaphragm, it's not going to sag down. Instead, the lungs are going to pull it back up. And when it pulls it back up, it makes the lungs smaller, increases the pressure, and pushes air out. Same with your ribs coming down and in. The elastic properties of the lungs are going to help pull those ribs back down and in. So you can exhale passively, right? Inhale, you got to contract muscles, and then just relax those muscles, and that air comes back out. But sometimes it's convenient to get that air out faster and get more of it out. Remember the respiratory lab we did? When you wanted to get your vital capacity, right? You were working hard, especially the forced expiratory volume, or FEV. You were trying to get that air out as much out as you can and as fast as you can. You weren't just letting things relax and squish back down. Instead, you were actively pushing that air out, squeezing down your lungs. And so there is also an active way to expire, or to exhale. To actively exhale, you also relax your inspiratory muscles. But you've got some other muscles that you can contract now to help accelerate the air leaving your lungs and to get more air out. For instance, your internal intercostal muscles. Those are deeper than your external intercostal muscles. Their fibers are arranged perpendicular to the outer layer, and they're going to actively pull your ribs down and in. And then you can also contract your abdominal muscles. Your abdominal muscles, though, those are around your abdomen. Your lungs are up in your thoracic cavity. What are these abdominal muscles? Do you know those muscles? Rectus abdominis is one of those sheets. Transverse abdominis. External obliques. And of course your internal obliques. So you got these 4 sheets of muscle all around your abdominal cavity. Well, what does contracting muscles down there have to do with getting air out of your lungs up top? I mean, they're totally separate. The diaphragm separates the two. What's the connection?
Pushing everything up, like the intestine up, and that's where it's going to air to go.
That's right. Remember, there's stuff down here. You've got large intestine, small intestine, liver, stomach. There's all kinds of stuff down there. And if you contract those sheets of muscle that are wrapped around all those organs, where are those organs going to go? Can they go down? Some situations they can, but for the most part, they're not going to go down. Okay? Let's assume you've got a strong pelvic floor. So they're not going to go down. Can they go back?
No.
No, why not? You've got vertebrae back there. Those ribs are going to keep things from squishing out. Are they going to go out the sides or the front? No, that's where these muscles are that are squeezing down on. The only place those organs are going to go is up. So you squeeze down your abdominal muscles, and then that pushes those organs up, pushing the diaphragm up, forcing it up. Remember when I was encouraging you to get as much vital capacity as you can, to bend over as you exhale, and that helps to push those organs up even more. So you compress them even more, helping to get more air out. All right. So if we're going to, oh, something's in my nose. All right, we'll just deal with it. So we're going to get all that air out. We're going to relax the diaphragm, and if we contract our abdominal muscles, these organs are going to push up underneath our lungs, and we're going to relax the external intercostal muscles, contract the internal intercostal muscles to pull those ribs down and in. All of that is making your lungs smaller, so that the pressure goes up, and so air is pushed out of your lungs into the atmosphere. Okay, questions about that? You now know how to breathe. All right, so here we've got those three pressures I mentioned before, noted on here. So there are a few gradients that are worth looking at. So we've got the pressure in the alveoli compared to the atmospheric pressure. Okay. Wherever it's higher, that's where the air is coming from, and it's going to wherever it's lower. So if we're going to inhale, we're going to drop the pressure in the alveoli, so air flows in. If we're going to exhale, we need to raise the pressure in the alveoli to push that air back out. And then there's that interpleural pressure. That pressure between the two layers of the pleura, that membrane that surrounds the lungs. All right, this pressure in here has to be lower than the pressure in the alveoli. It has to be a negative pressure. And what that does is it keeps those two layers stuck together. Imagine if you had those two layers and you blew in there to add some pressure. What would happen to those two layers? They'd start to pull apart. They'd increase their distance. And if those layers are too far apart, they're not going to stick together anymore. It's not going to hold the lungs to the thoracic cavity wall. They separate, and then your lungs collapse. That's bad news. So you're going to have a negative pressure in there. And if you go to try and separate those without adding any air in there, that's going to create an even more negative pressure. Boyle's law tells you that. If you try to expand that volume, the pressure drops. We start with such a small volume that any kind of movement drops the pressure a lot. So we're not going to be making big spaces in there. But if you pull on one of those membranes, the other one's going to follow because of that negative pressure in there. How does everybody feel about that? You're still not convinced. Anything to do with Boyle, you're not going to like, huh? No comment, okay. All right, let's go ahead and look at the respiratory cycle all the way through, and we're going to track the pressures and the volumes here. All right, so this is going to all be over time. Let's say 4 seconds to inhale and exhale. Here's the volume in our lungs, so we're going to inhale, and then we're going to exhale. So when the line goes up, that means the volume in our lungs goes up, line goes down, volume goes down. And now we've got some pressures in here. We're going to say that atmospheric pressure is at 0. This is all the pressures are relative to atmospheric pressure. We don't really care what it is. We just care how the other pressures vary compared to atmospheric pressure. This purple line represents the pressure in the alveoli. Notice that sometimes it's less than atmospheric pressure. That's when we're inhaling. And sometimes it's greater than atmospheric pressure. That's when we're exhaling. And then we have the interpleural pressure. Notice that's always negative compared to the atmosphere. Always lower than the alveolar pressure. That's going to keep those two layers stuck together. So we're going to go ahead and sort of walk through this, where these different numbers are, and see what's going on in each case, each situation. So we've got a little table here. We're going to track the pressure in the alveoli, the pressure in the interpleural space, and the volume of the alveoli. We're going to look at it at 0 seconds, first 2 seconds, 2 seconds, and so on.
What was the green line on the last image?
The green line, that's the pressure in the interpleural space between the two layers of the pleura. Okay? Everybody ready for the table? All right, so at 0 seconds, the very beginning of all this, we've already finished exhaling. We're done exhaling, and we're about to inhale, but we haven't started inhaling yet. Okay? So the pressure in the alveoli, what is that pressure going to be like relative to the atmosphere? Keep in mind that no air is leaving anymore, and no air is coming in yet. It's what?
Equal.
It's equal, right? If there's no airflow, assuming we didn't close our glottis off, we're going to keep it open during this whole time, then there's no pressure gradient. Because if there was a pressure gradient, there'd be airflow, but we don't have any airflow at this instant. Remember, this is where we're changing from exhaling to inhaling. The interpleural pressure. At this moment, it's at its highest pressure. It's at its maximum. It's still a negative pressure, but it's at its highest pressure. And let's think about what's going on anatomically. So we finished exhaling, so our lungs are as small as they're going to get for this cycle. We haven't started inhaling yet. So we're not pulling away from the lungs at all, we're coming in. And so we have the least amount of stress, you could think, between those two layers of the pleural membrane. When we start inhaling, we're going to try and pull those apart. We won't pull them apart, but we're going to try to, which will drop that pressure even more. But we haven't started that yet. So our lungs are relaxed, as small as they're going to be, so that interpleural pressure is as close to zero as it's going to be for this cycle. All right, in the volume of the alveoli, the volume of the lungs, but we haven't started inhaling yet, so we're at a minimum. This is as small as those lungs are going to be for this cycle. About the volume?
Yeah. About
So-
thorough in video. The last part of explain max and then again.
Max and min.
Yeah.
So max would be the greatest amount in the cycle. Min would be the minimum amount in the cycle. So for the interpleural pressure, it's at the highest pressure it's going to be. It's maximum pressure. But keep in mind, it's still a negative pressure. It's still less than all the other pressures. It's just not as less as it will be during the rest of the cycle.
Why is it the highest pressure?
Because we're not actively trying to pull the wall of the thoracic cavity away from the lungs, which they don't actually get away, but we're not pulling it away at all. Because when we do, then that's where we try to, or you would slightly increase that volume, which would drop that pressure even more, to make it even more negative. But we're not actively pulling away. We're about to, but we haven't yet. So it's, we haven't dropped the pressure as low as we're going to. It's still at the highest level. And then the volume of the lungs is at its minimum. We haven't started inhaling yet. We already got rid of as much air as we're going to for this cycle. We haven't started adding to it yet, so it's at its minimum. Okay? All right. So this is another publisher's version of the same thing we saw before. But we're at time equals 0 here, 0 seconds. We have not started inhaling yet. So we're done exhaling, haven't started inhaling yet. The pressure in the lungs equals atmospheric pressure. So this line here represents atmospheric pressure. So there's no airflow. And the pressure in the interpleural space is at its maximum. It's still a negative pressure, but it's as high, close to 0 as it's going to be for this cycle.